Let us now discuss how one gets a magnetic Hamiltonian involving only spins. We are particularly talking about Ising kind of Hamiltonians or Heisenberg kind of Hamiltonians. Mainly we would be talking about Ising Hamiltonians, where the spin can only have either pointing up or down. These are the two possible orientations, and let us see that how we can derive a Hamiltonian which we have introduced, or rather we have talked about when we spoke on magnetism during our lectures. So, we want to study magnetic Hamiltonian, and a derivation of a magnetic Hamiltonian would require that we know the addition of spins, or so say addition of two spins to and these are spin half particles. So, we have two spin half particles, and we would see that how one actually add the spin vectors. So, let us consider two particles with spin vectors S1 and S2. The total angular momentum what I mean by angular momentum is that the total spin angular momentum is S equal to S1 plus S2, where S1 and S2 are the spin vectors for the two particles that we are considering. So, just to remind you that both are spin half. Now, the direct product space is that consists of it's of four dimensions. So, the direct product space is 4-dimensional, and we can use the basis, use SMS basis for each. So, what I mean by that is that the eigenvalue for the spin operator S has eigenvalue S, and SZ has eigenvalue MS. So, we can form the basis of each of the particles by this SMS, and the total space will be product of two such SMSs, that is S1. So, total space is S1 MS1 and S2 MS2, and let the since we have for each one of them, so MS is equal to plus minus half H cross. So, let us represent the states by up and down. So, each of these half H will correspond to say up, and this minus half will correspond to minus half H cross. So, this H cross over 2 and this is minus H cross over 2, and hence we can write it in two ways. So, the space, the spin space or the direct product space is either you call it alpha 1. So, maybe this is called as the alpha and this is called as a beta, or so it's alpha 1, alpha 2, which means both are in upspin states, alpha 1, beta 2 means one of them in upspin, the other in downspin state, and alpha 2, beta 1, the first one is in the down and the second one is in up, or both of them are in the down. And this is one option. Whereas the other option is that we can write it as up, up as the states, up, down, and down, up, and down, down. Okay. So, this is other option, and we can simply choose one of them, but let us choose this option in order to write the wave function for the I mean to discuss this problem of 2 spins. So, what is the total value of MS, which is MS 1 plus MS 2, which can take value 1 0 0 minus 1, 1 when they both add up half plus half, and this is when half minus half, this is minus half half, and this is minus half minus half. And the total spin quantum number S, which is equal to S 1 plus S 2, which can take values 0 and 1. Okay. So, for S equal to 0, we have there is just one eigenfunction, and that eigenfunction let us write it with a form which is chi 0 0, which is equal to 1 over root 2, and I have a up down minus a down up. So, this is this is called as a singlet wave function, and this is antisymmetric. What I mean by antisymmetric is the following, that you have two particles. So, the first one is in up state, the second one is in down state. Here the second one, the first one is in down state and the second was is in up state. And now, if you interchange up to down, one gets a negative sign. So, this is that is why it is called as the antisymmetric. And for S equal to 1, we would need, so for S equal to 1, we will have 3 combinations, because we will have to take care of chi 1 1, which will be simply up state, chi 1 0, which will simply be a combination of up down plus a down up, and a chi 1 minus 1, which is equal to a down down state. Now, all these are called as triplet and triplet states, because there are 3 in number, and one can easily check that they are symmetric, because if the first particle is written swapped with the second particle, the wave function remains the same. So, these are the states or the wave functions for 2 particles, both spin half, and for a system consisting of or comprising of 2 spin half particles, and all possible combinations have been taken. We get 4 states, and those 4 states are 1 singlet and 3 triplet states. The singlet state is antisymmetric with respect to the change in the position of the particle, and the triplet states are symmetric with respect to the change in the position of the particle. So, these are the states, but what about the eigenvalues? Because in order to solve a full quantum mechanical problem, we need both the information on the eigenvalues and the eigenfunctions. So, let us see that so all these 3 states. So, now we will talk about the eigenvalues. These states are up, 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 down, down, up, and down, down. And so this forms the basis of the problem of a 2-particle problem, 2-particle spin half system. So, they are eigenstates of S1 square, S2 square, S1z and S2z. So, the total spin S can be 0 or 1. Okay. So, now we can see the how these total spin operators act on those each of these states. So, the total spin operator, which is Sz, which is equal to S1z plus S2z, that acting this state acting on or let us write it here as well. So, Sz acting on the up state, up, this will give me S1z will only act on the first spin on the left, and S2z will act on the spin on the right. So, this will give me H cross by 2 for each one of them, and I will get a H cross by 2 and up. So, as we have said that these are eigenstates of these operators. So, I get an eigenvalue equation, which is Sz acting on a up state gives me H cross by 2 as the eigenvalue and returns me the up state as well. Similarly, for Sz acting on up down would give me 0, because S1z will give me a plus H cross by 2 and Sz2 will give me a minus H cross by 2. And similarly, we will also have Sz acting on the down up state should also give me 0, and Sz now acting on the down state will give me a minus H cross. Sorry, there is a minus H cross by 2 for each. So, this should be simply H cross. So, this is for each one of them there is an H cross by 2. So, there are 2 H cross by 2s which make it H cross. So, Sz on down will give me a minus H cross and so on. So, these are the eigenvalues of these Sz operator. And what about so furthermore we have S square, which is equal to S1 square, which is S1 plus S2 whole square, which is equal to S1 square plus S2 square plus twice of S1 dot S2. S1 and S2 will commute with each other because they are they pertain to different particles. So, S1 square will be H cross, so it is half into half plus 1, half into half plus 1, this acting on. So, S square acting on any of these states. So, say we will talk about up say for example. So, this is equal to half into half plus 1, sorry, it is S into S plus 1. So, that is this, and then again for the S2 square this will be half into half plus 1. Now, we of course do not know the what is 2 S1 plus S2. So, we will leave it for the moment and let us see that what we can do for the S1 dot S2. So, S1 dot S2, if you see, it is equal to S1x S2x plus a S1y S2y S2y plus a S1z S2z. Now, if you introduce this ladder operators for the spins, so S plus can be written as Sx plus I Sy and S minus can be written as Sx minus I Sy. Now, this will give me S1 plus S2 minus plus S1 minus S2 plus, and then there will be a factor of half there and plus a S1z S2z. So, this is S1 dot S2 and hence what we can do is that we can see that S square acting on a up, which we have already saw that the first term gives 3/4 h cross square, second term gives 3/4 h cross square as well. Now, we have a 2 S1 dot S2. Now, for the up state, this will raise the spin and hence it will be 0 because up is the maximally aligned state, and though S2 minus can give you a non-zero contribution, but S1 plus will give 0 and similarly S2 plus will give 0, and that is why these two terms do not contribute, and that simplifies the problem, and then we are left with S1z S2z for which we know the operation. So, that is why we have done this, and this is 2 into h cross by 2, and this whole thing multiplied or rather acted upon by this. So, it is a eigenvalue equation, and this is, if you simplify it, it becomes equal to 2 h cross square up and so on. And similarly, for the down as well, one gets the same answer by doing the same technique. One gets this as so on these acting on the down state will give us a 2 h cross square and a down, and so they have, so these states up and down have total spin S equal to 1 and ms equal to plus minus h cross. Okay. But of course, S equal to 1 should have 3 states which are equal to ms plus minus h and 0. So, the third state, so ms equal to plus minus h is there. So, ms equal to 0 state is obtained by a particular operation. So, by the application of S minus on up state. Let us see how one gets it, or you can also consider or S plus on the down states. So, S plus S minus on the up state gives me S1 minus plus a S2 minus on the up state, which gives me, so S1 minus will lower this spin, and now this is something that you should have done in quantum mechanics. This gives me an eigenvalue, which is, these are not eigenstates of up, but it will operate on this and give me this S1 will give me a H cross and will give me up down, sorry, it will be a down up. The first one will lower, so it is a down up plus an up down. S2 will lower the other one, with an eigenvalue which is given by H cross. And so, 1 over H cross S minus up is nothing but 1 by root 2, which comes as a normalization factor, up down plus down up, does not matter, we have written down the second term ahead of the first term, and this will correspond to S z equal to 0. So, these three will be called as the triplet states, and so the singlet states are of course the which corresponds to so these are the triplet states. So, the two that is coming over here with spin s equal to 1 and m s equal to 1, which is here, and the other one comes from here. So, these are the three states, and now we will just look at the singlet state. So, which corresponds to s equal to 0, m s equal to 0. Let us just call it as we can call it as chi 0 0, or we can also use a notation which is like 0 0, which is equal to a half up down minus down up. So, why is it a singlet state? So, S z acting on this 0 0 will give me a 3 by 2. So, it is S 1 z plus S 2 z which will act on this. It will be a 3 by 2 h cross square minus 2 into h cross by 2 square minus h cross square acting on 0 0, and it will give me a 0 0 0. So, which means that m s value of this is equal to 0 and this has s equal to 0. So, we have found out all the 4 eigenstates of this 2 particle problem. So, let us now look at the spin Hamiltonian consisting of these. If we want to construct a Hamiltonian only consisting of these 2 spins, which is like a, as I said, like a Ising Hamiltonian or a Heisenberg Hamiltonian if S has a full rotational symmetry. So, let us just discuss the construction of a magnetic Hamiltonian. So, we have S square, which is equal to S 1 square plus S 2 square plus a 2 S 1 dot S 2. Now, the eigenvalue of S square is equal to 3 by 2 h cross square, as we have discussed that 3 by 2 comes from 2 terms of 3 by 4 h cross square, each of S 1 and S 2 and plus a 2 S 1 dot S 2. So, for the singlet state, that is S equal to 0, we will have to put S equal to 0, the S 1 dot S 2 has an eigenvalue which is equal to minus half minus 3/4 h cross square. because this is equal to 0. If you put the right hand side equal to 0, the S1 dot S2 will have an eigenvalue which is half of or minus of half of 3 by 2 h cross square, which is minus 3 by 4 h cross square. Whereas, for the triplet state, which corresponds to S equal to 1, so that will have 1 into 1 plus 1 h cross square for the left hand side, which is equal to 3 by 2 h cross square and plus twice of S1 dot S2. So, this is equal to 2. So, 2 h cross square minus 3 half h cross square divided by 2 is the eigenvalue for S1 dot S2 for the triplet state. So, this is equal to 2 minus 3 half is just half. So, this is equal to 1/4 h cross square. So, 1/4 h cross square is the eigenvalue, in short E value I am writing for the operator S1 dot S2 in the for a 2 particle problem. So, let us just summarize this quick result. So, for singlet states S1 dot S2, so this is singlet and triplet. So, this singlet one has minus 3 by 4 h cross square and this is 1/4 h cross square. So, this is the eigenvalue of S1 dot S2. Now, if we write down a Hamiltonian, which is H equal to 1/4 E s plus 3 E t. I will tell you what these are: E s minus E t S1 dot S2. We have written it in a particular way. This term where E s is the energy of the singlet state, and E t is the energy of the triplet state. And why have we written it in this fashion is that H acting on the singlet state, which is 0 0, will be simply equal to this 1/4 E s plus 3 E t and E s minus E t S1 dot S2 acting on 0 0. We can skip the comma in between. So, that is the singlet state. So, with E s equal to minus 3 by 4 h cross square and E t equal to 1/4 h cross square, one can simply check that H of 0 will give me a minus 3 by 4 h cross square 0 0, and similarly H acting on either of these up states or down states or up down plus down up states, all those multitude of down or up down plus down up down plus down up state with a normalization will give me a 1 by 4 h cross square and these states that we have written, such as up down up down plus down up. So, that says that we have arrived at a Hamiltonian which is which gives us, for a two particle problem, which gives us the correct energy eigenvalues for two spin half particles, for a system of two spin half particles. Okay. And this is that Hamiltonian. Now, you can see that if you if we redefine the 0 of the energy, we may omit the constant E s plus 3 E t by 4, which is common to all the states, all the 4 states. Then we can write down a spin Hamiltonian as H equal to J into S 1 dot S 2, where J is nothing but the difference between the singlet and the triplet energies. Here of course, we have the singlet energy to be lower, which is equal to minus 3 by 4 h cross square, and the E t being 1/4 h cross square. So, J will be negative. Now, if we say that such Hamiltonians can be written for n particles with a pairwise interaction between the particles, then we can write a generic Hamiltonian for a magnetic system or spin half system. We can extend it to spin having any values. It should be then it is a J, and then there is a S I dot S j, it is I and j, it is between the neighboring sides, and this is a Heisenberg Hamiltonian if S has a full rotational symmetry, and it is just the Ising Hamiltonian if S is taken as plus minus half. But however, it gives magnetic properties of the magnetic system, such as antiferromagnet or ferromagnet, and of course, if J is positive, now we are not restricting ourselves to only two particles where we know that J is negative, but we also go ahead and consider J to be positive as well. So, if J is positive in this particular model, in this Hamiltonian given by 1, 1 favors, we can write it with a minus sign, putting a minus sign from outside, then this favors parallel arrangement of spins, and which are essential for ferromagnetism. And if J is negative, then 1 favors anti-parallel arrangement, and it is antiferromagnetism is. We have seen these phenomena from a purely electronic model, which is Hubbard model, but however, we have also gotten exposed to this kind of spin only models which are which are there. So, if J is positive, then the energy is lowered. If the SI dot Sj, that is the SI and Sj, they point, the spin vectors point in the same direction, which are in a sense we talk about ferromagnetism. Whereas, if J is negative, then that means that the whole energy would be negative if Si and Sj are antiparallelly aligned, which are the features of antiferromagnetism. And so, this can be actually compared with the magnetic dipolar interaction. Like this, which is 1 over r cube, and it is a m1 dot m2. So, these are the two magnetic moments, and these are related. This you are familiar in the context of classical electromagnetic theory, and the relative distance where the relative distance between m1 and m2 are involved, but here we have a purely spin Hamiltonian, which neglects all spatial symmetries. Now, this is H written as J Si dot Sj has, there are a large number of approximations that are going on, namely Ij's are nearest neighbors. One does not have to be, one can include or longer than nearest neighbor, that is next to next nearest neighbor interactions as well. And we can also write this inside, the J to be inside, and it does not have to be constant, and it can depend from one bond to another. And so, these are possible Hamiltonians, and they have all been explored in the context of spin systems.